Welcome back, everyone. In part one of graphing polar functions, we learned about graphs of circles of the form r equal a cosine theta and r equal a sine theta. What we're going to do today is we're going to graph functions of the form r equal cosine n theta and r equal sine n theta. So we're going to change the coefficient in front of the angle. And just like last time, we are going to start by graphing Cartesian versions of those functions and then transfer that information to the polar graph. So let's start with y equal cosine 2x. As you know, the 2 has the effect of shrinking that graph of the cosine function horizontally by a factor of 1/2. And another way of looking at that is it decreases the period of the cosine function from 2 pi to pi. And so what we're going to do is the same thing we did last time, is graph critical values. As you know, the cosine is equal to 1 at 0. Cosine of 2x is also equal to 1 at 0. The cosine is equal to 0 at 90, but in this case it will be 0 at 45 degrees because of the horizontal shrink by a factor of 1/2. And continuing on in that way, the cosine of 2x will be equal to -1 at 90 degrees. It will be equal to 0 again at 135 degrees. It will be equal to +1 at 180 degrees, 0 at 225, and so on, and so on, and so on, until we get back to 360 degrees where it is 1 again. So we're going to transfer those points down here to our polar coordinate system, and then take a look at what happens in between those critical values. So at an angle of 0 degrees, the cosine of 2 theta is equal to 1. So we'll put a point right there. At 45 degrees, the cosine of 2 theta is 0, so we would put a point at the pole here. It's a little bit hard to see. But in between 0 and 45 degrees, you can look at the graph up above and you can see that y is decreasing, so from 1 towards 0. So the same thing is going to be true for r in our polar coordinate graph. So at 15 degrees, for example, r is close to 1, but it's getting smaller. At 30 degrees, we're getting even closer to 0. And by the time we get to 45, we're at 0. So our graph is going to look like that for angles between 0 and 45 degrees. For angles between 45 degrees and 90 degrees, r goes from 0 towards -1. And so what we're going to do, we've already got a point here at 45 degrees. We're going to plot a point at 90 degrees. So we go to 90 degrees, but we go the opposite direction because r is -1. And we're going to take a look and see what happens to angles, r values for angles between 45 and 90 degrees. At 60 degrees, if you look at the graph up above, you can see that r is negative, but close to 0, so we go in the opposite direction. We put a point close to 0 at r equal 75 degrees. R is getting closer to -1, so we go in the opposite direction and we put a point closer to -1 or closer to 1 unit away from the pole. And by the time we get to 90 degrees, we're at -1, so our graph is going to do that. Now for the interval from 90 degrees to 135 degrees, as you can see from the graph up above, r is at -1 at 90 degrees, but approaching 0 at 135 degrees. So we go to 105 degrees, for example, and we can see that r is close to -1, so we plot a point close to 1 unit away, but in the opposite direction of 105 degrees. And then as we go to 120 degrees, r is getting closer to 0, but still negative, and by the time we get to 135 degrees, we're back to 0. So our graph in our polar coordinate system is going to go like that. Between theta equal 135 degrees and 180 degrees, r is going from 0 to +1. So in our polar system at 135 degrees, we're at the pole. If we go to 150 degrees, r is at +1/2, or 1/2 unit away from the pole. At 165 degrees, we're almost to +1, and by the time we get to 180 degrees, we're back at +1. So our graph looks like that. Between 180 and 225 degrees, r is going to decrease from 1 to 0. So on our polar graph, at 195 degrees, for example, r is pretty close to 1, but not quite. At 210 degrees, we are going to be at 1/2, and if we continue on it that way until we get to 225 degrees, at 225 degrees, we'll be back at the pole. From 225 degrees to 270 degrees, r is decreasing from 0 towards -1. So at 240 degrees, for example, r is negative, but relatively close to 0. At r equal 255 degrees, r is closer to -1, and by the time we get to 270 degrees, r is equal to -1. So that portion of our polar graph is going to look like that. Between 270 degrees and 315 degrees, r is increasing from -1 back to 0. So if we go to 285 degrees, for example, r is going to be close to -1. So we put a point over here in the opposite direction. At 300 degrees, r is going to be -1/2. And by the time we get to 315 degrees, we are back at 0. And finally, the interval from 315 degrees to 360 degrees, we can see that r is increasing from 0 towards 1. So that portion of our graph is going to look like this. And we've finished up, and what we have here is a rose that is symmetric about the x and the y axis. It also has 4 petals, which is twice the number of the coefficient there, and the petals are length 1, which is equal to the coefficient out in front of our function. Now for the graph of r equals sine 2 theta. As you can see from the Cartesian graphs up above, y equals sine 2x is the same as the graph of y equal cosine 2x, except it's been shifted 45 degrees to the right. So in a similar manner, we will see when we graph r equals sine 2 theta that the petals of our rose have been shifted 45 degrees to the right, or in this case in the positive direction. So we will have petals of our rose, and the tips of those petals will be at 45 degrees, 135 degrees, 225 degrees, and 315 degrees. And you can verify this by checking those critical values and taking a look at what happens to the pattern, the y values, as we trace through the Cartesian graph above. So what we end up with is we end up with a graph that looks like this. Some things you will notice about the graph of r equals sine 2 theta is that it has 4 petals, twice the number of the coefficient of the angle. The length of each petal is 1, which is the coefficient in front of the sine function. And it has both x and y axis symmetry, similar to the graph of r equal cosine 2 theta. The next thing we want to do is investigate the effect of changing that coefficient in front of the angle. So we used 2 a few minutes ago, now we're going to change that to 3. So we can learn a lot by taking a look at the Cartesian coordinate system and that function y equal cosine 3x. Normally the period of a sine or cosine function is equal to 360 or 2 pi. So if we put a 3 in front of the angle, our period is going to be reduced by a factor of 1/3. So our new period is going to be 360 divided by 3, or every 120 degrees, the function is going to repeat itself. You can see that by looking at the maximum values of that cosine function, which occur every 120 degrees, which we can transfer down to the polar graph down at the bottom. So at 0 degrees, we'll be 1 unit away from the pole in the positive direction. At 120 degrees, 1 unit away in the positive direction. At 240, 1 unit away in the positive direction. We can also do the same thing with the minimum values of that function. So the graph of y equal cosine 3x has a minimum every 120 degrees, starting at 60, so then 180, and if we add 120 to that, we'll be at 300 degrees. And so if we go to plot those points, at 60 degrees, we should be at -1, which is actually going to put us back here at 240. At 180 degrees, we should be at -1, which is going to put us back here at 360. And 300 degrees, we're going to be at -1, which is going to put us back here at 120. So now we can take a look at what happens to the graph of r equal cosine 3 theta between 0 and 60 from the graph up above, that between 0 and 60 degrees, r changes from 1 to 0 to -1. So our graph in our polar system is going to go like that. Between 60 and 120 degrees, we can see that from the graph up above that r is going to go from -1 to +1. So our graph in our polar system is going to go like that. And we can continue on in that matter, going between +1 and -1 until we get back to that point right there, which is at 180 degrees. And then we can see that if we continue on, what's going to happen is we're just going to continue retracing our steps in our polar graph. So what we notice with our graph of r equal cosine 3 theta is that 3 actually tells us the number of petals that we have. The length of each petal is 1, which is the coefficient out in front. And the graph of r equal cosine 3 theta is symmetric about the x-axis. In a way similar that we dealt with the graph of r equals sine 2 theta, we're going to deal with the graph of r equals sine 3 theta. We see that r equals sine 3 theta is a horizontal shift of the graph of r equal cosine 3 theta by 30 degrees. So instead of having a petal at its longest point at 360 or 0 degrees, it will happen at 30 degrees and every 120 degrees after that. So at 150 degrees and then at 270 degrees. Otherwise, it's going to look identical to the graph of r equal cosine of 3 theta. So while we can always go back to the graphs of the corresponding Cartesian functions, it's good to recognize patterns with these polar functions. So what I'd like you to do is graph each of these polar functions on your calculator and then answer the questions down below. And below are the answers to those questions. Take some time, pause the video, make sure you understand the answers to each of these questions before you proceed.